All right, let me talk for a little bit here. So everybody should have gotten these six, right? Six resonance forms. The hybrid is one, one way of thinking about it is it's a mixture of all the resonance forms. And so each resonance form here, since there's six, contribute to the hybrid structure. And so the hybrid is thought to be a mixture of six resonance forms, and therefore this hybrid here consists of 1/6 part of this, 1/6 part of this, 1/6 part of this. In other words, it's 1/6 of each to make the hybrid. And that's what we end up with here. And so it's a combination of all these resonance forms. For nitrous oxide, this is what we come up with for the structures. Usually we try for symmetric structures, but that doesn't always hold true, because if we come up with different structures for this, like we'll go through the rules, and what structures do you come up with for this? Maybe we come up with like two double bonds like this. And so this gives us an octet. You guys remember counting the octet? We always have to remind ourselves, does this have an octet? When we look for an octet, we look at the total number of electrons surrounding it. And so visually, this is what I look for. Do we have an octet on this nitrogen? Yes. Do we have an octet on the oxygen? Now we have to double count because we're looking at just the total surrounding. And when we look at this oxygen, is there an octet surrounding the oxygen? Yes. And then over here, an octet. Yes, we should have an octet. We should not have more than an octet because this is nitrogen and oxygen. Oxygen and nitrogen cannot have more than 8 electrons surrounding it. Once we fill up that shell, it's done. So we cannot have more than an octet. It is possible to have less than an octet, but we try to avoid less than an octet because less than an octet makes it unstable. Like BF3, for example. BF3 was less than an octet. It made a powerful Lewis acid and very reactive. And so we try to avoid that. But this is one. This structure looks great. It has an octet. Everything looked good, right? Except for one thing. One thing looks bad. What looks bad about this structure? The formal charges look bad. When we look at the formal charges, what's the formal charge on the nitrogen? 2, 4, 6. So this nitrogen has a negative formal charge. This oxygen, 2, 4, plus 2. This nitrogen, 2, 4, 6, negative. And so the sum of the formal charges, minus 2 plus 2, 0. So that's fine, except the thing is, in order to generate the formal charge, you have to separate the electrons. So that means this nitrogen has to pull an electron off oxygen, and this nitrogen has to pull. And so two nitrogens each take a total of 2 electrons off oxygen. Does that sound very reasonable to you? Nitrogen taking electrons from oxygen? And not only just 1, but 2. Remember, the second ionization energy is much higher than the first. And so, in this case, the formal charges make this structure not look very good at all because, it just doesn't look like it would go. We could try something else. There are other ways of arranging the electrons here. We could have tried a triple bond here and a single bond here. Single bonds are a little longer. Triple bond. And then tried something like this. Again, here we have an octet. But what are the formal charges here? Are they better or even worse in this case? Well, taking a look here, what's the formal charge on this nitrogen? Minus 2. And oxygen? And this nitrogen? Does this look like a feasible thing to happen here? A nitrogen takes 2. One nitrogen takes 2 electrons from the it doesn't look so good. So we start looking for other structures, but we got to maintain octet, and there aren't any other really options here. These are 2 resonance forms here. These are what we call inequivalent resonance forms. Inequivalent resonance forms are different. If you look at each of these resonance forms, these are equivalent resonance forms. These have the same energy. All 6 of these structures are expected to have the exact same energy. However, these don't. Which one do you expect to be a little more stable? Or it's hard to tell, right? Or is it? Well, which one do you think would be a little bit more stable? The one on the left. So when we look at a hybrid structure like this, each of these contributes an equal amount to the hybrid. But if we were to draw a hybrid structure for these 2 resonance forms, then these 2 don't contribute equal amounts. One is a little more stable. And so I'd expect this one to be a little bit more stable than this one, so probably the hybrid is going to consist not of a 50-50 mix, but the mixture is going to be biased towards this. Here, slightly, because you'd expect this to be more stable. And so, normally it would just be a 50-50 mix if these were equal, but they aren't. But let's see, can we generate a better structure? Let me erase this. If we try the asymmetric skeleton, if we tried this skeleton, then we can come up with this structure here. And looking at this structure, this looks good. Octet, octet, octet. But what doesn't look so good are the formal charges, maybe. What's the formal charge on this nitrogen? The formal charge on this nitrogen? And the charge on this oxygen? No. Actually, I don't need to write the zeros. In this way, this one doesn't look so good because if we had a tug of war, one nitrogen pulls an electron off the other. Although these 2 nitrogens aren't the same because one's a bridging, the other's a terminal. But still, it's like, it doesn't look so great. Another option for this, where we can still maintain the octet, is maybe go like this. Still everything has an octet. It's just how we distribute the multiple bonds. So rather than 2 doubles, we'll go with a triple and a single. When we look at the formal charge, what's the formal charge here? Plus, minus. Well, comparing these 2, both are the same. Species has to pull an electron. But what do you think will have an easier time pulling an electron, nitrogen or oxygen? Oxygen. Oxygen is more electronegative, so this one we'd expect to be more stable than this one. Is there another one? Yeah, there's another one here. We did something like this. Again, everybody has an octet, so that's good, but what are the formal charges here? Formal charges would be -2 plus 1 plus 1. How does this one look to you? This one doesn't look good at all, does it? In fact, this one we'd expect to be unstable, and we're going to eliminate that as a possibility. And so this one looks like the best, right? This one looks like the best. But what's the electronegativity difference between oxygen and nitrogen? I'm not going to bring it up. Who's going to tell you? Oxygen's like a 3.5, nitrogen's like a 3.0 in terms of electronegativity. And so this is one other way of thinking about this structure is this. This oxygen and this nitrogen are going to be competing for this extra electron. And so if you have a nitrogen and oxygen competing for the extra electron, does the oxygen totally win? And let's say the oxygen comes out the winner and nitrogen comes out the loser. Well, it depends on the electronegativity difference. And so nitrogen is a 3.0, oxygen is a 3.5. So does that mean nitrogen is weak and going to completely lose? And so if we look at this, nitrogen has the electron, oxygen has the electron. And if there's a tug of war between nitrogen and oxygen, I'd expect it to be a closer match. I wouldn't expect one to dominate the other. And so, in other words, both of these are going to be contributors to the hybrid, but they're going to be uneven contributors. This is a better structure, but maybe this isn't so bad. And so let's just guesstimate. If nitrogen wins the electron versus oxygen, we'll just say maybe this is a 20% contributor, and this might be an 80% contributor. If that's the case, the hybrid might look something like this. If it's a 50-50, let's say if it's a 50-50 contributor, then what would it look like? Let's say these two were equal in energy. And so let's just do an aside here. If these were 50-50 contributors, then it would look like this, where this bond would be a 2.5 bond, and this bond would be a 1.5 bond. And then this oxygen would have a -1/2 charge, and this oxygen would have a -1/2 charge. But what if it were a 20-80 or 80-20? And so if it's a 20-80, then that means it's 80% like this. And so the structure is going to be biased towards this. And that means the negative charge here is more like -0.8, and the negative charge here is more like -0.2. And so the electron density spends more, or the electron cloud spends more time around oxygen than around nitrogen, because oxygen has a higher electronegativity. And so the bonding is going to be more like this than like this. And so this bond would be more like a 1.2 bond. And this bond would be more like a 2.8 bond. You see, so this is the case where we're going to have unequal contributions to the resonance hybrid here. This would be expected to be a negligible contributor because the stability of this is so low. Does that make sense? And so we started off with a very complicated one, and then went down. So let's take a look at a couple from experiment 9 first. This asymmetry thing is broken at times, and so we don't have to have symmetry. And so let's look at HNO2. HNO2, a lot of people will try to draw a very symmetric structure like this. That looks very nice and very symmetric, but this is wrong. The structure is asymmetric, like this. There's a rule that we have that didn't appear earlier. Acid hydrogens go on the most electronegative atom. So we have a choice. We could put the hydrogen on nitrogen or the hydrogen on oxygen. Well, oxygen is a lot more electronegative. Not a lot, 3.5 versus 3, but more. Oxygen is more electronegative, so the hydrogen goes on the oxygen, not on the nitrogen. And so it creates an asymmetry to the structure here. And so then we complete everything, and we end up with a structure that looks like this. when we look at the formal charges here, what are all the formal charges here? All the formal charges here are 0. Now we might think, okay, maybe I can draw a resonance form for this. So let's try that. Does this resonance form look okay? So I'm taking this lone pair and bonding it here. Does this resonance form look okay to you? Okay, how many people say it looks okay? Nobody? How many people say it looks very bad? How many people can't tell? Because this looks very bad to me. Why? Why does it look very bad to you?
Oxygen has more than octet.
Yeah, this oxygen has more than an octet. 2, 4, 6, 8, 10 electrons. This can't be. However, I might draw a resonance form that looks like this. Rather than taking this lone pair, I'll take this lone pair and bring it to the bond here. And then let's convert this so we don't exceed the octet rule. Let's do that. So we come up with this. How about this? Rather, we'll have the double bond on the left of the nitrogen rather than the right of the nitrogen. Does this look good? Yeah, everything has an octet, except this doesn't look so good because of the formal charges. The formal charge on this oxygen, 2, 3, 4, 5. Nitrogen, okay, 2, 4, 6, 7. This is minus. And so compare these two structures. Would you expect these to be equivalent resonance forms? No. In fact, you know what? This one, because of the formal charges, one oxygen winning, the other losing, it's unlikely that this is much. So we wouldn't have any resonance forms that we would draw for this because this one would be much higher in energy than this one. You know? Whereas these two are kind of comparable. You know, oxygen versus nitrogen in a tug of war, you know, on the opposite ends of the middle nitrogen. Whereas this wouldn't be, I mean, the formal charge is just too high, contribute much. And so this one, this is nitrous acid. We just have one structure for nitrous acid. All the acids are going to have the hydrogen bonded to the most electronegative element. Okay. Now, there are other things that pop up. One of the things that happens is that sometimes you get a structure in which you can expand the octet. So for example, SOCl2, is that one of the structures that we have? And so oftentimes we try to do something that looks symmetric. Is that what you come up with for SOCl2? Something like that? This one is good because this has octets, except it's bad because of the formal charges. The formal charge on oxygen is minus. The formal charge on sulfur is 2, 3, 4, 5 is positive. So it has an octet, but the formal charge is not minimized. What I mean by not minimized is we can minimize this formal charge if we do something. If we do what's called an expanded octet. If we expand the octet on sulfur, then it's possible to drop the formal charge down to 0. These are all zeros. But that means sulfur has to accommodate 2, 4, 6, 8, 10 electrons. Well, that's okay because sulfur is in the third period, and elements in the third period and lower can accommodate more. We'll talk more about this, why that is, or what other information there is. And so there are two. This one is expanded octet. And again, expanded octets are for third period and lower. And, lower in the periodic table, higher in the period. But the formal charge is minimized. And so what should we do? Should we leave the octet, or should we expand the octet? And typically what's done is you expand the octet. Typically, but sometimes we run into potential issues, which we'll talk about later. But, that's with a nice symmetric skeleton. If we do, oxygen is bridging as well. So if we did this skeleton, what are the formal charges here? Actually, they're all 0. Is this a resonance form here? No, this is what we'll call an isomer. Isomer has the same formula, different structure. So this is fine. Formal charge is minimized, everything has an octet. And so these are 3 structures that we can draw for SOCl2.